Alright guys, we're going to start talking about Earth movements or reasons for the seasons. And I want to start off right away by talking about two terms. One is rotation and the other is revolution. Now rotation is when we are discussing the Earth spinning on its own axis. Alright, so the Earth rotates or spins once every 24 hours, alright, approximately. And that's how we determine our day. Now, if we think about this for a moment, since the Earth is round, you see here it's nighttime, here it's daytime. The Earth is an oblate spheroid, but it's round, 360 degrees, and we know that it's going to spin a full 360 degrees in 24 hours. So what's that mean? If we do a little math here, is that the Earth is going to spin 15 degrees every hour. Alright, if we do 360 divided by 24. Now that means in 1 hour, this sunrise here is going to be 15 degrees over. And this is how we determine our time zones. If you take a look at this, these time zones are roughly split up every 15 degrees. You see it's not a very clean split. You look over here in Africa, it follows the borders of countries, and that's just to make it convenient for the people in those countries. But it's based upon the idea that we can split up time zones every 15 degrees. There's an hour difference because of the spin of the Earth. So that's rotation. The other one was revolution. Revolution, I'll write that up here. Revolution is the Earth moving around the sun once every approximately 365 days. So a revolution happens once every 365 days for Earth, whereas rotation is once every 24 hours. So if you think about it pretty logically, there's 365 rotations in one Earth revolution. Now these are kind of approximate numbers, 365. It depends on how you want to measure what a year is, which you'll kind of hear from people's projects coming up this week. And we'll get more into detail on that in class. But I just wanted to sort out those two definitions. Now, these big old eyes here have a purpose. I want to show you something. So take a moment. Alright, let's see. So here's the animation I want to show you. And I'll put a little, here's the web page here. And I like to look at this for a couple of different reasons. And I'll kind of go through and show you what they are. First off, it shows the reasons for the seasons. As you can see, compared to the sun, the Earth is tilted at a 23.5 degree angle. That's a number you should come to know. The Earth is tilted at a 23.5 degree angle. And because of that tilt, if I make the Earth begin to move here, and we get over to this part, that black line in the middle is the equator. Alright? The green line on top there is the Tropic of Cancer. And the green line below the equator is the Tropic of Capricorn. And the red line at the very top, the red circle, is the Arctic Circle. Now, I'm going to explain to you why we have these latitudes. All these years you've been learning about them, you're about to learn why we have them. So when the Earth is in this position and the northern hemisphere is tilted towards the sun, that more direct exposure to the sun, the angles of the sun are hitting the northern hemisphere at closer to a 90 degree angle. That causes it to get hotter in the northern hemisphere, and what do we have? Summertime. Southern hemisphere, we have winter time. Because of this, it's being pointed away. Now, on roughly June 21st, the summer solstice, that is the day when the sun rays hit the Earth at the Tropic of Cancer at exactly a 90 degree angle, right here. And it's the highest that the sun will hit the Earth in the northern hemisphere at a 90 degree angle. And that's where the Tropic of Cancer comes from. Also on this day, you'll notice, if you come up here to where the shadow is, or here's nighttime, here's daytime, you'll notice that right there, outlining that red circle, the Arctic Circle, the sun never sets. Alright, if you're on the Arctic Circle on June 21st, you will get 24 hours of daylight. For every step you take further towards the North Pole from the Arctic Circle, the more days you will get of daylight in a row. You get up further north, you can experience 2-3 months of 24 hours of daylight. The sun is never high in the sky Right? It's always going to be low on the horizon because you're so far north. So it's still, still stay pretty chilly. But that's what the Arctic Circle is all about. It's this whole area. Now, if we could see the Antarctic Circle down here, which they didn't outline on this animation, we'd see that they're experiencing 24 hours of darkness. Now, if we keep playing through this, you can see the shadow coming into the Arctic Circle. There's areas now that are getting daytime and nighttime. And we hit right here, September 21st. We are looking at the autumnal equinox. And right here is when the sun is hitting directly on the equator at a 90-degree angle. Fast forward some more, you start to notice that that shadow of nighttime is no longer letting any of that daylight into the Arctic Circle. So now the Arctic Circle up here is pointed away from the sun at such an angle that it is never going to experience the sun rise if you're on the Arctic Circle for at least one day on December 21st, December 22nd, the winter solstice. And the further you go up, the more days of night you experience. And here, the sun is going to be hitting the Tropic of Capricorn at a 90-degree angle. So they're going to experience summertime down here. We're going to be experiencing wintertime up in the northern hemisphere. And each day from December 21st or so onward, the days will get a little bit longer every day, a little bit longer, a little bit longer. You can see the sun coming up into the Arctic until eventually, boom, right here, March 21st, the vernal spring equinox. Once again, the sun is hitting the equator at a 90-degree angle. Alright, so here's another view of what you were just seeing in the animation. Again, the tilt of the Earth, that 23.5-degree tilt of the Earth, causes the northern or southern hemisphere to be tilted towards or away from the sun, and that is the reason for the seasons. That's what causes the seasons. So, when we're over here tilted towards the sun, the northern hemisphere is going to get more exposure, more direct exposure to the sun, and it's going to be warmer. And the southern hemisphere will get less, so it'll be colder, winter and summer. This is a really cool picture, I think. This is an analemma. And what this is all about, let me kind of explain the whole thing here to you. Way up top here, find a spot, way up here, that shows a picture, each one of these little circles, a picture of the sun at noon. On any given day of the year, throughout the whole year, someone came out, took a picture of the sun every week or two at noon of where the sun was compared to the town they lived in. Now up here, because the Earth was tilted toward the sun and it's summertime, the sun was higher in the sky. So this is summer right here. And more specifically, this is like June 21st, the summer solstice, when the sun is highest in the sky in the northern hemisphere. Now, as I took pictures, and we go through June, July, August, September, October, the sun at noontime keeps getting lower and lower in the sky. So what they're doing here is they're overlaying all of these pictures through a whole year on top of each other to show where the sun is at noon. And down here, when the sun is lowest in the sky, let's see if I can find my pointer here. There we are. Down here, where it's lowest, that's December. That's the winter solstice, December 21st. When it goes through this whole figure 8 cycle, through the whole analemma, that's what we call a tropical year. And you can see how with the summer sky, the sun being high in the sky, it's going to be a longer day, more direct exposure to the heat from the sun, and it's going to be warmer temperatures. Now, if I look at this, just seeing how low that noontime sun gets in December, that tells me that this town, wherever it is way up north, right, much further north than us. But you could do the same thing in the Rutland County area if you had a camera and the patience to do this through the year. Some globes actually put these on them, and we'll talk about this a little bit more in class too, because I know quite a few people are doing projects where they're making analemmatic sundials, and we'll be able to take a look at how those work. Alright, so in the past, some people may have believed or may have thought that the reason it gets warmer in the summertime here is because we're closer to the sun, which actually is not true. In July, we're actually further from the sun. It's called the day that we are the furthest from the sun, July 4th. It's called the aphelion. All right. So it comes to show, this comes to prove that it's not how far away from the sun you are. It's the fact that if that's our axis, that we're tilted towards the sun. That's why we're experiencing summer here, and down here they're getting less exposure and it's winter. Now, it's actually in January that we're at what's called the perihelion, which is the point in the year when the day that we are closest to the sun. That's going to be coming up January 3rd at 1 o'clock, 1 p.m. We'll have to look if that's a school day. We might have to kind of recognize that day. And again, we're pointed this direction. So since the northern hemisphere is pointed away, it's going to be winter time, summertime here. The summers in the southern hemisphere are probably going to be a bit more intense because they're closer and pointed towards it. And the winters are probably a little bit more intense because they're pointed away and further away. But ultimately, my point here is it's the tilt of the Earth and not the distance from the sun that is the reason for the seasons. Alright, I wanted to talk about one extra motion of the Earth, and this is so we've talked about rotation, we've talked about revolution. Now I want to talk about something completely different, and we call this precession. Precession is the idea that the axis does not point in the same direction all the time. That the Earth actually kind of wobbles. If you think of a spinning top, like the children's toy, as it gets spun, it's spinning, it's rotating really quickly. It'll begin to go in big circles as it revolves on the floor. As it starts to slow down, it'll begin to wobble. Well, the Earth kind of wobbles too. It wobbles on its axis, but it's a very slow wobble. It takes about 23,000 years. Some people estimate up to about 26,000 years to do one complete wobble. So I've been telling you that we're at a 23.5 degree angle, our axis is, compared to the sun. But that 23.5 degree angle, it'll wobble around and would be pointed at some point in the other direction. You can see how we are now. January, we're pointed away from the sun. And about 11,000 years from now, halfway through precession cycle, our January will look actually much different, right? So that brings up another point. In our last lecture, we talked about how our axis, the North Pole essentially, is pointing towards the North Star, Polaris, and that's why we could use that for a number of different things. We won't always be pointing towards Polaris. At some point, about 14,000 years from now, it won't be pointing towards Polaris at all. It'll be pointing towards another star called Vega, and that'll be our new North Star. And that basically sums up the idea of precession as it wobbles. And there's also been a lot of hypotheses about how the precession of the Earth may be directly or indirectly linked to ice ages. And I think there's still a long ways to go with that hypothesis, but it's kind of an interesting thought that we can talk more about in class. We'll end it there, and I'll see you in class. Bye-bye.